The William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us at the university as well as online, we thank the USDOT very much for their ongoing support. It's greatly appreciated. We also, let me welcome those of you who are joining us via the internet today, which includes representatives from METRA, Parsons, Federal Railroad Administration, Trans Systems, and several other organizations. And let me remind those of you participating either in person or online, if you would like to receive PDHs for your participation, please send Emma an email with your information as described in the email seminar announcement. I also have an announcement I wanted to make before we introduce our speaker, which is I just learned this morning that one of our own, Dr. Rapiq Sat, has been voted by Progressive Railroading Magazine as one of the rising stars in the rail industry. And so this is a great honor for him. It looks like he's not here today, but nevertheless, I'd like to offer a round of applause for him. He's a highly deserving individual, which has played a major role in rail tech success for the last 6 or 7 years at least, as well as doing a fantastic job leading our railroad safety and risk group, which I know many of the students here are participants in that. All right. Well, turnouts and crossings, collectively known as special work, play an indispensable role in the function of the rail network. They are also the most expensive elements of the track structure. Thus, it's ironic that they are subject to the most damage. They represent an ongoing maintenance challenge to railroads because of the interference such maintenance causes to operations and because of the expense involved. Consequently, AAR has devoted considerable attention to research on improving existing designs as well as exploration of new concepts. The leader of this research for over 20 years is our speaker today, so we're very fortunate to have him speak to us about it. Mr. David Davis is a senior scientist for the AAR's research organization, the Transportation Technology Center in Pueblo, Colorado. Dave is one of ours. He's an alumnus. He received both his BS and MS degrees here in civil engineering. And actually, while he was still in college, he began his railroad career working as a track laborer during the summers for the CNNW Railroad outside of Chicago. It obviously got into his blood because following completion of his studies, he accepted a full-time position as a research engineer with the AAR at their Chicago Technical Center. He rose through positions of increasing responsibility at AAR, and in 1998 moved to TTCI out in Colorado when they consolidated all their research activities there. He's a professional engineer in the state of Illinois, former chairman of the TRB Committee on Railroad Track Structure System Design, served as committee coordinator for the AAR Engineering Research Committee, and is a long-standing member of the ARIMA Committee on Track. He also serves as the supervisor for the AAR Technology Outreach Program that sponsors rail research here at the U of I. Please join me in welcoming our speaker today, David Davis, who will present the William Hay Railroad Engineering Seminar entitled Advanced Designs to Improve the Performance of Special Track Work. Turned on?
Yes. Okay. I think we're good to go. Well, good afternoon, everyone. It's always a pleasure to come back here to my academic roots, and I'm very happy to talk to you about work that we've done for the industry in the areas of special track work. So I'll talk about projects that have been cooperative between the AAR, the Association of American Railroads, and the Federal Railway Administration, and then some that are strictly funded by the AAR. So, in the area of special track work, this is a very unique area in that it combines a lot of different departments from the railroad. We're working on things that are related to operations, vehicle dynamics, and my favorite, materials and more traditional civil engineering. So in this area, we obviously would like to have all the components wear out after serving a long life. But what we find is that we still have a lot of places where fatigue, failures, sudden failures that can cause operational issues still occur. Excuse me. On the safety side, special track work is typically the third leading track-related cause of accidents. Number one is typically rail flaw failures, and number two is general track geometry. Special track work is number three typically. And so we see failures that are related to the operation, the moving parts of the turnout, and then also materials issues. These components tend to be highly sensitive to dynamic wheel load. So this is an area where the railroads do spend a lot of money, typically more than $1 billion a year in the U.S. alone. Unlike some other areas, it's really, the pie is divided up into three main pieces. You have the direct costs of purchasing new components, the capital costs. You also have a large maintenance component. And then in addition, we have a train operations or a train delay component, which is fairly significant in this area and may not be in some of the other track component areas. So in general, spending north of $1 billion, and maintenance and train delay more than half of the total. So just buying the best components is essential, but is not sufficient to have a cost-effective operation. There's some good news here in that we see the failure modes are changing over time, and we think that's because the components are getting better. And so while fatigue failures are still significant, we do see that more and more are wear-outs than we used to see in the past. In addition, running surface profile maintenance is becoming a bigger issue. This is a good thing because it means that we've eliminated some of the other failure modes that tend to occur first. So instead of the frog breaking, now we see that we get to the point where we're having to grind flow off of it. And so that takes up a bigger part of the maintenance budget. So that's a good story, actually. So every few years we survey the railroads and we look at how various track components are performing. In this case, we looked at turnouts. And from that, we determined what the major failure modes were at the time. And then we began to address those with our research program. So in the area of turnouts, or the switch end of the turnout, in fact, if you look at the accident statistics, most of the issues are related to the switch, the moving rails part of the turnout, rather than the frog end. And so the top 5 switch-related accident causes as of about 15 years ago are shown on the slide. So the upper picture shows a typical chipped out switch point. So this is a fatigue failure. Whoops, if I learn how to use this. Shown right here where the thin section of the point fails. Also shown on the bottom photo in the same way. So this is obviously a potential safety risk because a wheel coming along can actually climb that switch point, and the flange can get in that notch and more easily climb out, causing an accident. So this is a major issue for the railroads. Going down the list, dragging equipment derailments. Well, this is the turnout just being the hapless victim of a wheel that's already off. And so you see that a lot on higher speed main lines. So that's difficult to solve in designing a turnout better. Moving down the list, surface and alignment defects. Certainly they become perhaps more important when you already have a change in the direction of the train and going through a turnout. And then worn switch points, again, we can get wear so that the contact with the wheel is such that it facilitates a derailment. So there should be wear limits on switches, and those are now difficult to measure in the field. And then split switches. This would be a failure of the operation of the switch to fully close to one alignment or the other. And so that can occur. That's usually a yard type derailment. So looking at those failure modes, switch point chipping was by far and away the red X, the number one on the Pareto chart. And so just looking at the cross-section of a typical yard switch, which is a knife edge point, shown here on the left, a very thin section, you can see why these might fatigue under high axle loads. Also notice the section is dynamically unstable, if you will, in that if you apply a wheel load, this is likely to rotate under load. And so that rotating actually causes some bending stresses which tend to break the point of the switch, the top of the switch. Shown in the middle is a great innovation in special track work of many, many years ago. It's a Samson undercut type switch point. So the tip of the switch is a lot thicker. And we've removed metal from the stock rail to accommodate that. But still you can see where this is a delicate component, if you will, for a heavy axle load freight operation. Moving on. If you remember the basics of track alignment layout for the rest of the railroad, when we have a curve, we align the tangent alignment to the curve, as shown in the upper photo, but of course we make things a little better by having a transition curve in there, a spiral. And so by doing that, the rate of change of acceleration and force in the vehicle is spread out over a longer distance. Okay, so what do we do on turnouts? Turnouts, we do the opposite. Turnouts, we offset the two alignments in North America. The typical ARIMA switch, the alignment of the curved portion of the turnout is actually outside of the tangent alignment. Okay, so why do we do this? Well, it makes for a much shorter turnout, and it allows the switch point to be robust, thicker, so that we don't have to machine something that's down to, a couple of molecules wide. And so for manufacturing reasons of 100 years ago, this was a good idea. The resultant is that you get a switch that has a kink or an alignment defect, if you will, right at the point of switch with an entry angle that's fairly large. And that large entry angle, of course, causes us some issues in terms of performance of the vehicles going over the turnout. Also, of course, in a turnout, we typically don't have super elevation that we would have in the rest of the curves out on the railroad. So for those reasons alone, turnouts tend to perform pretty poorly as far as vehicle dynamics compared to the rest of the railroad. When you, the key to look at on this slide is we've shown you a plot of measured lateral force on a loaded coal gondola versus distance into a turnout. And so that big entry angle that we talked about on the previous slide results in a fairly high lateral pulse, shown on this slide for the ½ degree entry angle turnout, which would be a typical ARIMA style number 20 turnout operated at 40 miles an hour. You can see that we're generating a lateral pulse that's around 15,000 pounds. So that results in quick wear and fatigue of that switch point, and thus some of the damage we saw on the earlier slides. We can fix this with better alignments, and so that's what the industry has looked at in the last few years. The sort of the sticking point is that, believe it or not, we rate the turnout for speed based on the the steady state curving force that occurs behind that entry. And if you make the entry angle smaller, you make the radius of the curve behind it smaller for the same length turnout, and thus you have a lower allowable speed, even though it's a better performing turnout. So for some regulatory issues, this has inhibited the use of better switch designs and turnout alignments in North America. So our company and the various Trackwork suppliers have looked at how to improve the performance of switches by lowering the entry angle. And various things have been implemented. Use of spiral geometry, use of the so-called pseudo-tangential turnouts, which follow an alignment just like the rest of the railroad, where the curve and the tangent are aligned. They're tangential. But then you just chop off the end of the switch point when it gets to be a very thin section. Those work very well. There are limitations, though, that are practical limitations. Shown here on the slide is a number 6 1/4 inch heel spread. So this would dictate the length of that switch point. And so there are practical issues on transporting a switch point when they get to be more than about 60 feet. And so we're kept in a box where we can't have a switch point really that's much longer than 60 feet if you're trying to transport it to a remote location. So there are a lot of design limitations on what we can do, but the bottom line is anything we can do to make the entry angle smaller at the beginning of the switch will provide for a much better ride and typically longer-lived components. We've also looked at revising the stock rail. And if you look at switch point chipping very carefully, what you find is that it's really related to deformation of the stock rail, the matching stock rail. And so we've looked at ways to revise that profile on the stock rail to minimize metal flow under traffic. We've also looked at revising the switch point running surface profile to make it look more like the rest of the railroad and having the shape of a worn rail. And that's proven to be quite effective. And then we've also looked at ways to alter the switch alignment so that wheels don't come in contact with the thin section of the switch point. And then finally, one that's a little bit out of the box, we looked at how to eliminate the switch point entirely from the mainline route of the turnout. So if you match wheels with rails and apply loads in a vehicle dynamics type model, then look at the stresses that are generated through finite element analysis, you find that they're behaving how you would expect them to behave. You get high contact in this gauge corner, and that causes flow of the stock rail downward towards the switch point. And then we get a mating surface here, a matchup that's not ideal. We tend to have contact just at the top. That causes the fatigue that we see in the switch points. A little bit more evidence of that. With the help of various railroads, CSX and the BNSF in particular, we went out and measured many worn switch points. I don't know if it shows up too well in the photo here on the left, but that's part of the switch point up there, and then it's broken out from there going forward. It's pretty much all chipped out here. So this is in a yard application. We measured many profiles on switch points and stock rail pairs matched up. And I've offset the stock rail in this case, but you can see this would be a time series or a distance series of switch point profiles on a switch such as this one. I'm not sure it is this one exactly. But the thing that we tumbled to after looking at a lot of these is they all break at the same height, all switch points, no matter what thickness it is. And why does it do that? Well, that's where the flow on the stock rail is making contact. So it's really flow on the stock rail which is causing a lot of our issues with the fit up of the switch point and the adverse bending stresses that we see. So the fix there is to allow some wear in that matchup of the stock rail and the switch point. We also looked at rolling contact fatigue on switch points. And what we see is that typically in this transfer zone back here where the wheel is transitioning from the stock rail to the switch point, we get a lot of rolling contact fatigue. The vehicle's trying to steer there. It's suddenly changing its contact location from stock rail to switch point. And so this is a very severe service environment for the steel in this area. In addition, we have a legacy issue in that switch points were machined, they were planed from full section rails. They're still made that way, but typically it's done with a CNC type machine rather than a planing operation. But in the good old days, a planing operation made sense, and so a simple profile was all they could accomplish. So they would basically give the rail a flat top haircut here and give you this nice flat surface that would quickly deform into something that looked more like the red line on the upper plot there. And so in doing that, we're doing a lot of work and we're removing a lot of material from wear under load. And so if we start with something more like this, we see that we have to do a lot less maintenance grinding, and we can delay the onset of rolling contact fatigue, spalling, it's sometimes called on the railroad, the head checks. We can delay that by a significant amount of tonnage. And so we came up, we being the industry, our company led the effort, but we worked closely with our colleagues on the railroads, the track standards engineers, and then also the suppliers. We came up with a profile that tries to match a worn rail. And so if you remember, most rail sections have a three radius corner by design, and then a 78-degree side slope that matches the wheel flange. We thought that was a bit much ambition for the first step, so what we did was we came up with sort of the poor man's approach to that. We only had to buy one cutter to do this, so we came up with a 1-inch radius corner. And to show you the law of unintended consequences, we gave this sort of sketch to the supplier, the manufacturer at Progress Rail. And we said, we want a 1-inch radius, but we want a discontinuity here. However, you need to come in and touch grind that to smooth it. Well, they took our instructions and they said, oh, okay, well, we can rotate that 1-inch radius. We can move the center of that curve, and we can actually make it a nice smooth corner. Well, that kind of ruined the design, but they thought they were making an improvement for us. But we were not specific enough in what we wanted. So we actually do want this to have a bit of a kink in it, because this orientation matches a worn wheel gauge throat much better. Anyway, we worked our way through those issues, but the first prototype was not quite right. Anyway, with the help of BNSF and UP, we were able to make some number 20 switch points and put them in mainline service. So I got to go to some exciting places like Marceline, Missouri, and Bonner Springs, Kansas, to test these out. So this is on the Santa Fe Transcon. It's a crossover, number 20 crossover. This turnout had the revised profile, and the other one had the railroad standard profile at the time. Same thing at Bonner Springs. UP actually put in 2 sets of crossovers, one each with the profile, the new profile, and their existing design. So we went out and periodically took measurements using a digital profilometer, a mini prof, to measure how those switches were wearing. what we found was quite encouraging. Shown on this plot, we've got the new profile, new, and then after, I forget how much tonnage, but a fair amount of tonnage, 30, 40 MGT probably. And then here, this was one of the standard ones, comparing how it wore over that same tonnage interval. So you can see a fairly significant improvement in the wear on these components. The scales on here, pardon me, I think they're millimeters on both axes. And the bar chart kind of sums it up. The prototypes were wearing less than half as much as the standard profiles. Also encouraging, the contact is where we want it. On a typical switch point, it's right on the gauge corner. And so that's a very high contact stress. In the new profile, it's on the top of the switch point where we want it. And that causes less deformation, less warping of the switch point under load, and also lower contact stresses. The standard points started to show rolling contact fatigue after about 100 million gross tons. Again, I apologize if you can't see it in the picture. It's kind of in the shadow part there where you see the typical spalls. A lot of people call them spalls out on the railroad. And the prototype looked pretty clean in general. This would be, this is not 23 feet back in the switch. This is measurement location 23, which I think, yeah, is around 14, 15 feet.
Dave, just to confirm, those are both in the same crossover? They're just two different turnouts in the same crossover?
They are, yeah. These are the ones on the BNSF at Marceline, Missouri. Boyhood home of Walt Disney. All right. So moving on. Conclusions. A simplified profile works pretty well. This was presented at ARIMA in 2012. Significant reduction in wear that continues to today. So we're out a couple hundred MGT on these now. The prototype that was closer to the actual intended design worked pretty well. In 2012, the railroads were studying whether the 3-radius design is feasible. The answer is yes, and virtually every railroad uses that 3-radius design today. So that's become an industry standard. Okay. Next, we'll talk a little about vehicle dynamics. So we're looking at ways to avoid the wheel flange coming in contact with the thin end of the switch point. This can be accomplished, and it can be accomplished in several ways. One way that we looked at was in modifying track gauge so that we get the vehicle to steer away from either switch point, depending on which route you're going down. We were able to do this by lengthening the switch points so that we actually get the wheels on the switch points before the point of switch. So typically a switch point starts at the point of switch, which would be back up here in this drawing. And what we learned is that if we get the wheel set on the switch point earlier, that we can control it better, and that by manipulating track gauge, small changes in track gauge, we can make the vehicle steer the way we want it to. And so we can get it to steer away from the switch point and have lower forces as it encounters the switch point. So here's a slide I hope will show what we're trying to accomplish. So if, as you understand, our wheel set is got a solid axle. This is not your car with a differential. And so how does a vehicle steer? How does a wheel set steer? Well, hopefully we have a cone-shaped profile on the wheel. And so the wheel set can steer by shifting laterally within the gauge of the track. And so we're trying to apply that concept to our turnout. And so by moving one of the rails out, we can get this wheel set to want to steer back in this direction to the right, because obviously as that axle makes a revolution, the radius on this wheel is bigger than the radius over here. So for every revolution down the track, this wheel is going further than that wheel. So it's steering to the right. And so by manipulating track gauge in the turnout, we think we can steer away from the switch point tip on either side. We've modeled this, and then we've measured the actual performance. Shown here is a modeling. So the part we're trying to affect is that we have a switch point that begins here where you see this big lateral spike. And this is actually a wheel set angle of attack. And the difference between the conventional and our design is this little piece right here. So we're just barely getting the wheel set to have an angle of attack that's negative, to be away from the rail. And by doing that, we greatly reduce the wear and the forces in that area. Shown the plot on the right is the predicted wheel lateral force versus distance, with the switch starting here at about 30 feet on this plot. So you can see the conventional ones show the bigger forces. In this case, as much as 25,000 pounds under a 315K car. Whereas the pre-steer switch, as we're calling it, shows lower forces. It also shows the location where that force peak happens is perhaps a different location. But remember, we made the switch point longer in that case. So it's occurring actually about the same place in the turnout, but our switch point starts sooner. The good thing about this is it seems to work for a wide variety of wheel profiles. And so we're able to get a benefit for the typical worn wheels out in track, not just the new AAR 1 in 20 tread type profile. So complications, how can this go wrong? Well, the wheel set is doing its own thing, and it is basically oscillating within the gauge of the track as it goes down nice nominal tangent track with good wheel sets. The individual wheel sets do this. It's damped out a bit by the truck, the fact that we have two wheel sets coupled together through a truck structure. But how can this go wrong is that if we have our switch point here where we have a big angle of attack on the wheel, this isn't going to work too good. If we're here, it can work better, certainly. So we don't see a pure improvement of all wheel sets. Some of them approach a switch with a bad angle of attack to begin with, and there's not much we can do about those. But for the great average, a pre-steer arrangement where we widen out track gauge to get away from the switch point works quite well. All right, so we actually built a number 20 and tested it at our FAST facility in Colorado. The good news is we are seeing a decrease in maximum lateral forces. If you measure them, I think I've shown 99th percentile. It's about 12% for a loaded car at 40 miles an hour. The bad news is that we seem to be wearing out the stock rail. And so this requires a little bit more thinking on our part. Perhaps we're asking too much of the wheel set to make this big change in angle of attack. And so we're not sure if it's the trouble with doing turnout testing is we have a sample of 1. So I can't tell you for sure whether it was something wrong with this stock rail or it's something wrong with our design. We think it's mostly our design. And so we are changing out that stock rail. We're adjusting the relative height of the switch point and the stock rail. In other words, we're putting a little bit bigger point slope on our switch point, and we'll see what happens. So this one is not ready for revenue service, but still looks promising. If you were at the REMA Fall Conference in 2013, there was a paper by my colleague, Dr. Hsu, myself, Blaine Peterson from voestalpine, and Sung Lee from the FRA. And this concept was applied to high-speed turnouts. And so they looked at how they could improve the ride quality on turnouts that were designed for 120 miles an hour diverging. And they've applied our concept of the pre-steer, changing the track gauge in the switch. They compared several different geometries of switch, of turnout alignment, and one of them was our pre-steer with a spiral, constant radius curve in the middle, and another spiral out. The takeaway is, yeah, you can improve even the best European designs for high-speed turnouts. And so our pre-steer actually does better than the others in terms of L over V ratio, in terms of the amount of load on each wheel, and whether the vehicle unloads as it goes through a curve. And then this is also a measure of ride quality. So if you're on a high-speed train, don't ride on the power car because you're going to feel a little bit uncomfortable, at least according to the international rules. But the coach, the passenger coach, has much better ride quality. This is more like a freight car, actually. So don't ride in there if you can avoid it. Anyway, it also predicts much lower wear on the switch point. So what we're seeing in our freight test, we think would apply also at very high speeds. All right, the next one is a little bit more out of the box. So one way to avoid failure of switch points would be to eliminate them from the mainline route. And so that's what we've done here with the help of Burlington Northern Santa Fe and Progress Rail. So if you see one of these turnouts, you'd think somebody screwed up here, but that's actually the intended design. So it's yeah. So it's also known as a continuous mainline rail turnout. So the same rail all the way through. We have a lift frog back here, which again the rail is continuous, and through the switch. So for 99% of traffic, the intended use. Nice smooth ride, no change in profile, no change in track stiffness. They really perform very well. BNSF now has about 10 of them out in revenue service. Shown here in the picture on the left is the switch thrown for the siding. So this is an aggregate, a company that makes various like cold mix asphalt products. So they get aggregates shipped in. So it gets fairly high use. But this is the intended niche for this product would be in places where the vast majority of the traffic is mainline, and an occasional car is put in the siding. So it's also known as a vertical switch because essentially the two alignments are overlapping, but they're offset vertically. And hopefully I can show you how it works with some videos here going forward. So again, a niche product. The stock rails are very robust. The ride quality is excellent. And the mainline, or the diverging traffic, is limited to 10 miles an hour as a result. Okay. So this wasn't our great idea, but we steal shamelessly from the past. Here's a catalog picture from 1920s. And so this design was actually used in that period of time. I don't think many were still in service in 1920, but they were used quite a bit in the late 1800s. It was easier to make work back then because the rails were a lot smaller and the wheels were essentially the same size as they are today. So again, how does this thing work? Well, in our current conventional switches, we have one switch point on each route, and the two are connected together and they throw together typically. So this is called a split switch for that reason. The continuous rails are on the outside. And then this was a prototype that BNSF had built. It was tested at FAST in 2012. So again, the switch points are both on the field, are both on the diverging route. One on the field side, one on the one more conventional on the gauge side of the track. So we did modeling to prove whether this concept would or wouldn't work and perhaps what the limits of application were. So we did our vehicle dynamics modeling. We said there would be a bit of a vertical bump in going up and over the mainline rail. And we'll show you some video of how that works. But laterally, it should perform very well. And it has so far. So for the main line, it looks like regular open track, lateral loads less than 2 kips. So we tested various parts and pieces to see how to do this. The smart people at Progress Rail came up with a good way to do it, and so we adopted their approach, and that's what the railroads are currently using today. We wanted to avoid this kind of situation where we had to machine material off of a stock rail and weaken a stock rail to do this because there's not that much traffic going down the diverging route. So we tested various parts and pieces. We convinced ourselves it would work, and then we, the industry, implemented it. So we'll show you some video of the prototype and test out at FAST at Pueblo, Colorado. So this slide says purpose of the, whoops, maybe it won't work. There we go. Okay. So obviously this was for the executive types to understand what's the purpose of this thing. It's so that most of the trains going on the main line have a nice smooth ride. So that video is not all that exciting, but we'll go on to the next. So here we've got some vehicles being put into the siding track, into the pocket track. First car is an empty, and then it's followed by some loaded 315s. So the way this works is that field side point picks up the wheel so that the flange can clear the continuous mainline rail, and then the gauge side point diverts the wheel set laterally into the siding. Hopefully you can see the trucks are kind of, they're pitching as they climb up that little ramp and then back down. Next one, this is from our track loading vehicle. So we're actually applying a gauge spreading load to the car as it goes through the turnout. So you'll see again looking backwards at a facing point diverging move through the turnout. As the video gets towards the turnout, it'll go into slow motion. So this wheel set is flanging because we're applying a gauge spreading force. We wanted to see what would happen with a bad steering vehicle. And so here we come to there'll be a joint bar, and then we'll actually go on to the switch. And note how as the flange clears the mainline rail, then the wheel set comes over. So we think it'll work for cars that have bad steering, which is the kind of car you'd probably be putting in a set-out track, one of the intended uses for this kind of turnout. And then here's one that shows the vehicle essentially going over the top of us as we're looking down the middle of the track. So again, if you look at the right-hand wheel, you can see that it's raising up on that switch point till it can clear the mainline stock rail. And then the left-hand switch point has the same ramp to it, and it's the one that's guiding the wheel down the diverging route. Yeah. Well, it always amazes me when you look at the wheel rail contact that it is a tiny little patch on there. Okay, so for the analytical types, we measured forces. We compared it to a more capable number 20 turnout. This is a number 11 on our continuous mainline rail turnout. And the takeaway is, as shown on the slide, for the diverging route, the lateral forces are similar. The vertical forces are a bit higher as you go up and down that ramp at the beginning. But we're limited to 10 miles an hour. That's our intended use for the diverging route. For the mainline route, it behaves like open track. And so we get significant force reductions at both the switch and the frog in the lateral plane. There's no guardrail. And then vertical forces also go down because we're using a lift frog, a better designed frog that has continuous running surface for the main. So this is the way to go for those occasionally used sidings off the main. Our proof test at FAST showed there were some things that needed improvement. This is a whole new concept, so the spreader bars, the spreader rods on the turnout need to do more. And the initial design had sort of a weak spot in it, shown by these two rocks here, where there's spreader bars, throw rods for the switch up front, but then when we get back to the fixed heel, there's this length where the rail is largely unsupported laterally. For a conventional switch, of course, the switch point is supported laterally because you have a stock rail that's fixed to the field side of it. But in this case, it's reversed, and we didn't think about that enough. Good thing we tested it in a proof test mode at FAST. So anyway, those are some of the improvements that were made to the ones that are now out in revenue service. We also measured wear on the components. As you can see, these shapes are not very conformal. Hopefully you can see that. It's just a flat top angle, essentially, on that switch point. It's like an angle bar. And so we saw higher wear, as you would expect. A second order improvement would be to make those running surfaces more conformal. What is the practical effect of having that? Probably not much. We do see that the wear, again, you have to be careful showing this kind of slide to management. The wear rates are hundreds, perhaps 100 times higher than we see on the matching stock rail. Oh my God, the world's ending. No. Again, very little traffic down the diverging side. And so that 100 times more wear, this is a year of wear out on the BNSF. So mini-prof profiles taken in a time series, that's how much wear we have on that switch point. It is 100 times more than the stock rail, but it's almost infinitesimal. It says we'll get a very long life.
Yeah. To say this in another way, so you're saying the rate of wear is 100 times higher.
It is.
But the traffic is thousands of times lower.
100 times less, yeah.
So.
Yeah. So we don't expect the wear of the switch point to be the failure mode, if you will, of the turnout. But again, you cannot apply this to a place where you're going to run half the traffic down the diverging side. Here's a garden spot of the world, Vaughn, New Mexico. And for anyone who's been there, I hear you laughing. Okay. Actually, it's eastern New Mexico. It's actually kind of pretty there. But Vaughn is a high spot, and so it gets all the bad weather. Oops. I apologize. Let me see if I can run the video. This just shows a stack train going at 70 miles per hour over one of these turnouts. And so hopefully, well, maybe not. Okay, I broke it. Sorry. Anyway, it's just a cool video. It just shows one of the turnouts. Thank you. Thank you. So Vaughn, this is east of Vaughn, or west of Vaughn, New Mexico. And hopefully the takeaway is you can see the mainline move looks just like open track. The containers are not rocking back and forth. There's no vehicle dynamics going on. The 4 at Vaughn, there's two double-ended set-out tracks. They've been in there about a year. And so far so good. They're performing very well.
Dave?
Yes, sir.
I remember when, a few years ago, when what I'll call the jump frog was coming in, you were doing the research on that. I remember seeing some numbers from you that there were thousands of potential applications for those. Are the numbers similar for this, for the switch end of it?
We think it's a smaller market. We do. But along the same sort of applications. We think that the lift frogs actually are more durable because of the material. It's a manganese casting, and so the wear rate differential is not nearly as big.
I'm also guessing that this switch is more expensive than the conventional, or not?
It really should not be. However, they are, because they've only made 10 of them. Yeah, so they're trying to recover the R&D cost. So we think long-term they should not be more expensive. Essentially what we have is a funny-looking manganese tip on them, if you will, and not much else different. Okay, next topic. We've looked at how to smooth out some of the stiffness variations in the turnout. In this case, we're looking vertically. And so Canadian Pacific Railway was kind enough to donate a number 20 turnout to us at FAST for heavy axle load testing. And because they did that, we were able to buy a second switch for that turnout and test some of these new concepts. So we worked with pad suppliers to provide pads under the bottom of the concrete, or in this case, timber ties. And so by doing that, we were able to add, to level out the vertical stiffness through the turnout. Because as you would expect, as you go back in the turnout, you get these bigger cross ties. The turnout gets stiffer. And then at places like where we have the frog, where we have multiple tie plates covering more than one tie, and we have the extra guardrails and whatnot, that part of the turnout typically is very stiff compared to everything around it. So this is a picture in the upper right showing the pads on the bottom of our number 20 timber tie turnout that CP Rail donated. And then this is the turnout in track. We had measured, over the years, we had measured the track stiffness around our loop, and so we knew it pretty well. And we knew that there were certain turnout design features that created hard spots in the track. So an RBM frog with all the additional plate work and the big casting is typically a very stiff location. And then also hollow steel ties weren't a particularly good match with timber tie turnouts. The supplier says they are a good match with concrete, and I believe that's probably true. But for timber, it created some hard spots. And so we installed this turnout and compared it to the previous turnout, which had almost the same alignment, same design features, except for these under tie pads. And red is the one without pads. Green shows the turnout with pads. So we were able to reduce the stiffness variation in the turnout by a considerable amount. We think that should result in a longer surface life, as well as making all the components last longer. It also will help us in trying to eliminate that one of those top 5 switch failure causes of having surface and alignment defects in the turnout.
Dave?
Yes.
Can we go back to that previous? So I'm colorblind, so when you said the red, are those the squares or the triangles?
The red are the squares.
So I guess I'm confused because there's that one peak at about 150.
Yes.
Well, I guess I misunderstood.
That's the RBM frog.
Okay, so we don't, but what are the green triangles then?
The green triangles are this turnout with the pads. It's the same design turnout. It's got the same RBM frog. It's got the same switch. So if you looked at the statistics on this, the variation for the green for the triangles is much less than the variation for the red squares.
I'm sorry, I misheard you. I thought you said the opposite. Okay, never mind. Sorry.
No problem. No problem. Okay. So there were other complications with the experiment. I won't go into those at this point. They didn't really affect the result. We were doing some alignment tests at the same time. So cutting to the chase, this is a plot showing the average settlement, top of rail settlement for the turnout versus tonnage. This is without the pads. This is with the pads. So the takeaway was about a third less settlement over the first 75, 80 MGT. We've gone out well past 200 MGT, and the settlement rate rolls over as the track consolidates. But this ratio has held. So we were able to reduce settlement by about a third. We get much more uniform stiffness in the turnout. And more importantly, the differential settlement, tie to tie, has been reduced by more than 33%. It's more like 2/3. And it's that differential settlement that triggers the railroad having to go out and surface the turnout. So this is a big success. The question is, of course, the economics. How long will these pads last? And we don't have an answer yet. Next, we'll talk a little bit about high-angle frogs and crossing diamonds. And so we did some work for the Federal Railroad Administration in looking at how to affect performance of crossing diamonds by changing the foundation underneath them. That was the original purpose of the test. And so we built some test panels, and we ran a series of tests where we measured wheel rail forces in going over various foundations. We kind of had an idea about the superstructure and how to change that too, so we implemented that as part of this test. So we did a lot of side-by-side comparisons where we milled a flangeway in a continuous rail. So we just milled out a flangeway to generate impacts. And on the other side, we made something that looks more like a 3-rail diamond. We actually cut the rail all the way through and then applied joint bars and a spacer in there to keep the gap the same on both sides. We ran a various foundations underneath here with things with ballast, ballastless track, big rubber pads, variety. And we saw that we could affect the foundation. We could affect forces due to the foundation variations as shown on these two plots. But the two lines are this milled gap versus a cut rail. And what we found was the cut rail generated much lower forces. So we think we're getting some structural damping, if you will. We're getting some damping that helps, and that we get differential movement of those two pieces as the wheel goes across. So this side doesn't deflect until the wheel's on it, whereas this side is already deflecting with the wheel going left to right. So at first we didn't believe this. We thought, oh, those instrumentation guys screwed up again. And so we turned our test car and we ran the opposite direction, and we still got the same result. So we thought it was something with the wheel sets, but turns out this actually happens. And so we went back and tried to model it, and sure enough, it's a big effect. So we really want to design a more flexible frog. The problem is nobody likes bolts. Nobody likes a lot of little pieces out there. And so, you know, how to do this and make it maintainable is really the issue. With the help of Nortrack, Voestalpine, we were able to take an existing crossing diamond design known as a straight rail reversible casting diamond. So this one's unique in that it's kind of loosey-goosey to begin with. It has lots of pieces, and each frog is made up of actually 4 castings, and then they're all bolted together. So our brilliant idea was, well, don't bolt them all together. Allow one side to move relative to the other to replicate what we had seen in our previous tests. It works well. Works great for the first train, doesn't work so great for the 1000th train. Because as you can guess, if you give it all these degrees of freedom, it's going to like pull itself apart. And so we want vertical movement, but we don't want longitudinal movement. So anyway, hopefully the next slide here will kind of illustrate that. So over the years, we've tested a variety of crossing diamonds with different angles. And if we add that, you can see there's a big angle effect. There's a big speed effect, obviously. But if we add that flexibility, we can actually reduce forces. This is a 78-degree diamond with flexibility. This is one that doesn't have that flexibility in it. So we can have a fairly big effect. Going back to the previous slide, you also see that kind of blue stuff in there. So we added some rail seat pads that, again, provide a little more deflection under load and a little bit of damping. And those pads proved to be quite useful. So this is the crossing diamond without the pads, the top line here, and then with the pads. So a fairly big difference in dynamic loads. And then as we add our further refinement of the vertical split spacers, which allow additional movement, the effect was pretty small. Those are the other lines on the plot here. So this is a big deal. It says for the same dynamic loads that the railroad has now at about 20 miles an hour, with these pads you could go perhaps as high as 40 miles an hour. So that's a big deal. That would be reducing a lot of slow orders out on the railroad. All right. That's my current home out in beautiful Colorado. I'd be happy to answer any questions. I'm sure I confused everybody with some of this, but thank you for your attention. I appreciate it.
We do have time for some questions.
Yes, sir.
By the way, have you tested the displacement of the pound switch for the continuous mainline switch? I mean, have you tested the displacement of the point of switch for the continuous mainline switch? Have you tested the displacement due to the temperature variation?
Due to temperature variation.
Of the displacement of the point of the rail, the blade?
Yes.
Longitudinal,
yes, we have.
Okay.
It's relatively unimportant for the vertical switch because we don't have an undercut, we don't have any change to the stock rail, and so as long as we've got room for travel of the rods in the ballast between ties, it's good to go.
Okay.
The alignment is not critical. It's a very high diverging angle to begin with, and so it's actually more tolerant of longitudinal movement than a conventional split switch.
The result within the standard or the specification, the result is good?
Yeah, it's still within spec.
Okay.
Yeah.
Thank you.
Thank you.
Other questions? Back.
Whatever happened to the long-term viability of the high-speed flange-bearing diamond?
I would describe it as they're a technical success. It's not clear they're an economic success. So there are a couple of issues with them. One is that because they are unique, there's been now 15 of them in service, that they're still kind of custom. They're not a mass production product, so the first cost is high. The second issue is the wear on the flange-bearing surface. And that has been significantly higher than expected from our testing. In our testing, we saw that the wheels became fairly conformal to that shape of the running surface in a hurry. But out in revenue service, because there aren't enough of these yet, the wear rate does not decrease with time, as it did in our testing. One of the things we're looking at, the railroads, the suppliers, decided to make the running surface flat in cross-section. It's just a straight line across. And what we had recommended was something conformal to the wheel flange to begin with. So to make it with a fairly large radius concave upward, so that it would lower contact stresses from the beginning. The current replacement diamonds that are going in track now have that feature. And what we've seen is the initial deformation, which was as much as a 1/4 inch in the first 20 mGT, is reduced to about 10% of that. So by making it conformal to begin with, I think we're going to get a much longer service life. Whether they're economic for many applications is yet to be determined. But at least the first ones did not appear to give a particular economic benefit to the track department. It obviously reduced forces on the vehicles. Yes?
I guess I'm surprised to hear that. I'm not doubting you. I just remember, you know, for years I've been hearing what a high maintenance item traditional diamonds were. So do the flange bearing diamonds still have high maintenance, or just there's so much higher initial cost that it's hard to cost justify them?
I guess I want to be politically correct here.
Okay.
It depends on which pocket it comes out of. So if it comes out of the capital budget, that's not good. If it comes out of the maintenance budget, we're already used to doing that. So that's actually what flange bearing did. It traded capital for maintenance. And that was not necessarily popular amongst all railroads.
Okay. What do you call the turnout you were describing? I'm forgetting the
Continuous mainline rail turnout?
Yes, continuous mainline. Are there any regulatory hurdles you have to overcome with those, or not?
No. The frog is allowed to be flange bearing for 10 miles an hour, so as long as you're limited to 10 miles an hour. The switch does not have any regulatory issues other than you would need to educate potential inspectors that as that switch point rises, until it gets to be more than 5/8 tall, track gauge is still defined by the mainline rails.
Okay.
And so if you were to take a tape from the gauge side switch point to the field side switch point, you would say it's wide gauge, but it actually isn't, because it's the mainline stock rail that's a definer of gauge. So there needs to be a little bit of education on that. It's the same issue we have in a fixed point frog. If you went out and measured track gauge right before the point, you'd say, this doesn't meet. Well, everybody knows it does. It's just that that location cannot have a point right there.
Right.
So,
other question? Okay.
Have you do any work about simulation or testing for the temperature force distribution within the continuous mainline turnout, like the temperature force distribution, which is very important?
we have not, but longitudinal force issues and turnouts in general are the next thing we're working on.
Because when it welded in with the turnout switch, the distribution just changed due to the stopper spacing.
Yes.
So
Yes, we've done another failure mode survey with the railroads this year, and what jumps to the top now is rail running, longitudinal force issues, with turnouts.
okay.
And so we are looking at how to control that better. We in North America went to a floating heel block on the switch, and the floating heel block generally works well, but it does cause us some problems where the switch points will move relative to the cross ties until they bind on the cross ties, the throw rods. And so we don't see that so much in other parts of the world where they have a lot more expansion joints in the track, And in a lot of cases, they use a mechanical heel on the switch.
10 years ago, when I was a student, we did this kind of calculation and test for the temperature force, longitudinal displacement, and especially for the redisplacement. For example, like the mechanical heels, stoppers, and especially for the TTCI location, because temperature maybe variation is huge. So I think this is a part of the new prototype of the Turnout. Very good for the future stability of the track as well as for Turnout.
Yes, we've looked at, for example, putting the throw rods, the spreader rods, above the cross ties.
Yeah.
And when you do that, then you can have a lot more rail running back and forth without having a problem. It solves the operating department's problem. It doesn't solve the track guy's problem because the rails are still running.
Yeah, because the temperature force for the turnout, especially for the point of the switch, they transferred to the stock rails. So there's different with
Right.
the main rail.
Right. So as they move relative to each other again, it messes up the matchup between the two.
There's some of the interactions of the mainline and the turnout.
Yes. Yes. Very important topic. Yes.
I had a question about the work you're doing with the under tie pads. So it looks like they may have some useful applications for like the transition zones and things like that you were discussing. But I guess my question is, first of all, how long approximately do you expect one pad to actually last in service? I know that they've been used a bit more with like concrete ties, so maybe if there's information on that. And then the second question is, how would you even go about replacing those? Because presumably if they wear out, then are you going to have to take out the entire like switch section in order to replace the ties or the pads underneath?
Yes. Changing out switch ties is no fun, especially in interlockings, on elevated structures and whatnot. So the only answer I can give you so far on service life is that we've run 200 plus million gross tons on that number 20. After about 150, we pulled a tie out of each panel of the switch. So, a 16-footer from the frog all the way up to the switch end. The good news is when we pulled the tie, the pads came with it, and they were still in one piece. Hooray. You could see indentations. You could see like micro cracks in them, but indentations from individual ballast particles. But in general, I would say they've still got a lot of their life left. Ours is a dry environment. This was a one-of-a-kind. So the supplier essentially took a nail gun and nailed these pads onto our timber ties. And so far, they're holding on. We would expect that the bigger benefit is with concrete tie turnouts. And there you could cast them into the tie. You could interlock them physically into the tie. And so we expect a bigger benefit, and we expect they would be more durable under that condition.
Thank you.
Any more questions? Well, if not, yeah, thank you.
All right.